Okay, so we are waiting around 5 minutes for others to come. And do you have any problem with the project or any case study or other stuff? So related to the group projects. We have broad topics and become more flexible. So either you want to design a robot or improve the existing design, or we want to design components or any factors or multi-robot system. If you want to just design a robotic system, or you can just do a task-based problem like using implementation of vision system for grabbing or we can place stuff. So all the questions are open. And now you just find topics that you're interested in, not to be like innovation or novelty, always fine. Yeah, but just do a research background and all the topics are fine. Yeah. So I think this loading will be much less than before, because previously, I think 2 weeks ago, when we introduced the projects, we said that you need to design a new robot, but I know because your time limitations and also you are new to the robotic background, so maybe design a new robot may be very hard task for you. So now just find a problem and solve the problem. So all the topics are. So today we will be going through the sensor actuator 2. So it's basically on the actuators. And these are the syllabus, I think. Today will be 3 groups going to present their case study. And so actually for the robot components, for this section, it's just an introduction. So it's just to let you know what are the common sensors or common actuators that's used in the robots, and just for your background study. So I will go through really fast for these sections. And after that, to a position application for continuous information matrices, and that will be the start of the robotic modeling. So from here to, I think, to the static and stiffness analysis, here are the main fundamental mechanical modeling for robotics. So I will go through slower so that you can follow how to do mechanical jobs. So this is the definition of actuators. So actuator is a mechanical device for moving or controlling a mechanism or systems. So typically it's just take energy. So it's like using air or like electric current or liquid, and you need to do some motions or you need to prevent moving. So this is the actuator. So these are the common actuators in robotics. So I think many of you know the electric motors and the hydraulic. And this is the soft pneumatic actuator. It's a new in the soft robotics. So like you can use in the silicone or other stuff, and you just use the pressure of the air and you will expand and doing the deformations. So that's this kind of robot move or doing the actuators. And these are some interesting actuators, but it's not really common. So like thermomagnetic motors, ultrasonic or piezoelectric motors. So this is the thermomagnetic motors, and this is the piezoelectric motors. So it just translates the electrical back to mechanical. So these are the electrical motors. So the electrical motor is an electric machine that converts electrical energy into mechanical energy. So it's So it just as the definitions. So I think all of you are familiar with the motors. And these are the three types of motors. So this is the DC motors and the AC motors and stepper motors. So there are mainly two types of AC motors, the brushed and brushless. And now we'll just quickly go through the principle of the DC motors to let you know how it works. Because DC motor is one of the very common actuators we use in robotics. So the main components is apertures and also the magnetic field and also the commutator and the brush. These are the brush and the commutators, and this is the armature. And the permanent magnet provide a stationary magnetic field. So I think what we know is that the current, when the current flows through here and it passes through the magnetic field, and it will generate a torque to move this armature, rotates, and after that when it rotates to here, it will change by the brush. So these are the steps that of a brushed DC motors. So starts here. So when the coil is powered, a magnetic field is generated around the armature. So here has a magnetic field, and the armature is pushed away from here. So because it's a current and magnetic, and the armature continues to rotate. And after when it passes through here, so it becomes horizontal line. The commutator reverse the direction of currents, because here is have a brush and commutator. So as the direction of the currents reverse, then the motors can continue to rotate. So these are the advantages and disadvantages. So a DC motor is low initial cost and high reliability, and it's simple control of motor speed, just like doing the higher voltage. Sorry. And the disadvantages for the brush DC motors is high maintenance and low lifespan when high intensity uses, and the maintenance involves regular replacing, because the brush and spring, we need to replace that. And when it comes to the brushless DC motors, so a typical brushless DC motor use rotating permanent magnet in the water, and a stationary electric current magnet on the motor housing for segments. So after we will see a figure, we will explain. Okay, so I think we're going to have a figure for this. So I'll just go through very quick. So advantage of the brushless motors will be a long lifespan, little or no maintenance, high efficiency. But the disadvantage will be high initial cost and more complex motor speed for the controllers. So for in total, so the DC motors provide excellent speed control for acceleration and decelerations, and it's easy to understand design. So the design is very easy, and it's simple, cheap drive design. But the disadvantage is high maintenance compared to other actuators. And this is the AC motors. So it's like the DC motor is direct current. It's driven by the alternating current. So it's commonly consisting of two basic parts: the outside stationary stackers and also and the inside rotors. So these are the graph of the AC motors. So you can see outside we have the stators, and inside we will have the roller. The roller inside and the stator. So this is the outer frame and the stator and the winding. So just three-phase motor winding, so you can produce different magnetic field. So the advantage of the AC motor is low cost, speed variations. So since the speed of the AC motor is controlled by the frequency, so it's low maintenance. But the disadvantage of the AC motor is inability to operate at slow speed and poor positioning control, and also the limited speed through the frequency supply. So I think the speed limit of the AC motor is constrained by the frequency of the current. So compared with the DC and AC motors, DC motors are usually seen in application where the motor's speed needs to be external controlled. So it's a lot of DC motors are used in our robotic applications. And AC motors work best in application where the power performance is sort of extended period of time. So it's usually when you start an AC motor, you want it to run for a long time. So DC motors are single phase, but AC motor can be single phase or two phase. And the AC and DC motors use the same principle of armature winding and magnetic field. So this is how it's generate torque. And we come to the stepper motors. So the stepper motor is brushless, synchronous electric motors that can provide a full rotation to large number of steps. So there are three types of stepper motors, but we will focus on variable reluctance. So the motor position can be controlled precisely without any feedback mechanisms. So because it is rotating step by step, so when the step size is designed, it is determined when you design this step. And we'll have a short video to introduce this set of motors.
How does a robotic arm in a manufacturing facility repeat the exact same movements over and over? How does an automated milling machine move with such precision? It's all because of the stepper motor. What's special about the stepper motor is that it can control the angular position of the rotor without a closed feedback loop. It is a simple, accurate, and open loop system. Let's first understand how the variable reluctance type of stepper motor works, which is the simplest one. Later on, we will move to a highly accurate and commonly used motor type. This motor has 6 stator teeth and can be energized with 3 separate DC power sources. The rotor is made of a stack of steel laminations. It has a different number of teeth than the rotor, 4 in this case. This is done intentionally so that only one pair of rotor teeth is aligned with the stator at a time. You can explain how this stepper motor works by yourself. If you de-energize coil A and energize B, it becomes clear that the rotor will rotate as shown. From the geometry, it is clear that the one-step size is 30 degrees. To get the next step, de-energize coil B and energize C. After that, coil A becomes energized again. In short, the rotor moves to the position with the least reluctance. The step size of this motor is 30 degrees. You can improve the accuracy to 15 degrees with a small trick. When coil A is energized, the rotor is in this position. We know that when coil B is energized, it moves 30 degrees. What happens when coils A and B are energized together? The rotor will come to a position between these two cases, or it will move 15 degrees. After this, de-energize A. Then, after reaching B, This kind of operation is known as half-stepping. The motor we have been discussing is called a variable reluctance motor. The most versatile and commonly used stepper motor is the hybrid motor type. Let's explore the functioning of a typical 1.8 degree step-size hybrid motor. The hybrid motor has an axially magnetized rotor with toothed steel caps. So one end of the rotor becomes the north pole and the other end becomes the south pole. The accuracy of this motor lies in the clever arrangement of the rotor and stator teeth. Let's understand it first. The rotor has 50 teeth. To understand the stator teeth arrangement, first assume that the stator has 50 teeth as well. However, the stator actually has 2 fewer teeth than the rotor. So we are left with 48 teeth. Let's arrange the 48 teeth into 4 group pairs as shown. Now let's realign these groups. The green set moves so that it is half aligned with the rotor. The teeth of the yellow group are completely unaligned with the rotor teeth. The blue group is half aligned with the rotor. The red group remains in place. In short, the red set is completely aligned with the rotor, while the yellow set is unaligned. The other 2 sets are half aligned. Please remember that the rotor head facing you acts like the south pole. The stator coils are connected as shown. They are 2 independent coil sets. When set A is energized, the stator forms a magnetized pattern as shown. One pair of stator poles acts as the north pole and the other as the south pole. As the opposite poles attract, they will be aligned. The same polarity poles will be unaligned. When the coil B is energized, observe what happens to the rotor. It has to rotate by a small angle in order to align with the new north pole. It is clear that this angle is 1/4 of the angular pitch. In other words, the rotor moves by 1.8 degrees.
So I think all of you have known how the principle of the stepper motors. So that soft iron multi teeth rotors with on the status. So the stepper motor is related to both the number of stator teeth and the rotor teeth. So it's shown. And this is the pulling torque and the pull-out torque. So the pulling torque is the maximum torque against which a motor will start. So basically it's saying that the pulling torque is the maximum torque that can drive these stepper motors when the external torque is loaded from start to run. And the pull-out torque is when the motor is running. So this is the maximum torque, that external torque that these stepper motors can perform. And we come to the hydraulic actuators. Hydraulic actuators uses the power of a pressurized fluid, and the mechanical engine is converted to hydraulic energy. Hydraulic system can be controlled almost as accurate as an electrical motors, but in general, electrical motor is more accurate than the hydraulic pump. And this is a typical hydraulic system figure. So we will have a pump, a motor, so the motor will do the pump, and we'll have a fluid tank, and this is the accumulator. So these are the advantages of hydraulic systems. So usually more powerful than electrical actuators. So if you have the mechanical parking lot, they usually use the hydraulic systems to transfer the cars for leveling. And although electric motors can be equipped with gearbox, high power and high ratio gearbox tend to be very inefficient, expensive, and hard to maintain. And one hydraulic system can drive multiple units, as everyone knows that the pressure can, if you have different tunnels, then the fluid can flow to different tunnels and given the same pressure to the different area. So one hydraulic system can drive multiple units, and the other linear motions does not need. So basically, it is linear motions when you press and you will generate the linear motions. But for the motors, it usually use the rotational motions, and we need to use the mechanism to transfer the rotational motion into the linear motions. And it's relatively easier maintenance procedures, and we not need cooling because it is fluid and have self-lubricant and relatively safe. And these are the disadvantages of the hydraulic systems. So it's lower efficiency, require a reservoir of fluids, so you need a tank, and it's non-linear in nature because it is you're using the pressure, and it's risk of leaking. And multiple actuator synchronization can be very complex, and it tends to be more noisy. So this is for the environment. And this is for the actuator part. I think some of you didn't hear just now. So we have changed our, we have broadened our project's topics. So to become more flexible and to more open topics. So you just choose one of the topics you want to do, or others is okay. You just need to be in the robotic system field. So you can design a robot. You can improve existing design, and you can design components or entry factors and so on. And also you can design robot systems, such as multi-robots, and you can just doing task-based problems. You don't need to do any design, and you can just implement vision, the camera, and doing the pick and place problems. But just you need to define the problems in the field of robotics. So that's all you want. And you need to apply mathematical modeling, such as forward kinematics, inverse kinematics, Jacobian, static analysis. This will be taught. We will be teaching this module, this class. And if you have other mathematical modeling, it's welcome. If you are doing vision systems, so it's welcome to just give in the mathematical model. And you need to conduct literature reviews, so you need to explain the background. So I think that's all for the final project. So it's more flexible than before, because I think 2 weeks ago, we stabilized and you need to design a new robot, or you need to have some innovations or like this kind of stuff, because I know this is a master modules. We do not need to have this regulation is so strict, so we're more flexible to our final projects. So I think this comes to our main topics in the robotic. So I will go slower for these sections. So this is the position and orientation, and this is the homogeneous transformations. So these are all the configuration of the robots. And this is reverse again. And today we'll go through the position, orientation, and homogeneous transformation. So let's start. Like this is a reference frame, A. So it can be written as RFA. And this is the reference frame B. And so it's written as the R. So from here, from this reference frame to this frame to B frame, it will undergo both the translation, the position, the displacements, and the rotation, the orientation, the rotation matrix. So the explain part is the position and the orientation. So we'll start with the projection. So in the plane space, this is a vector, and here we'll have a theta, this angle. And for the projection in the 2D space, project on the x-axis, this is the length, and project on the y-axis, this is the length. And for spatial case, so it's in 3D. So this is the 3D vector. So we'll have x-axis, y-axis, and z-axis. So the projection will be A, B, C, respectively. Is this speed okay? So now we're going to find the orientation of a frame. So starting from this A frame and B frame, A frame will, as you can see, is in the blue line, and B frame will be in the red line. And it rotates about the z-axis, so you can see the xb become xb prime and yb become yb prime, and this is theta. So how do we write the rotation matrix for this? So it's simply the projection of xb. So the projection of xb, so maybe should be written xb prime, yb prime, and zb on the xa, ya, za. So we can try it out. So the xb projection on the xa, xb projection on the xa, so it's cosine theta. And the xb on the ya, so it's sine theta. And at the z-axis is 0. And for yb, the projection on the x-axis is, I think it's minus sine. And yb at x, ya, so I think it's sine. And z is 0. And because z is, we rotate about the z-axis, z never change, so it's the same. And this is the rotational matrix for rotating about the z-axis for theta angle. And this matrix, we can write it as RAB or RAB. So it's both we can write. So we can write this. So this is the B frame with respect to the A frame. And if we written in the mathematical process, so these are all vectors. So you just multiply it together, and then you can get this one. And this is the orthonormal matrix. So because it's always at 90 degrees one another, so we can say this independent to the other vector. So it's orthonormal. And in the rotational matrix, this is the column for A and for Y and for B. And if you do rotates about the x-axis and y-axis and z-axis, you can get these three rotational metrics. Just now we rotate about the z-axis, so you can see it's the same. So it's cosine sine 0 minus sine cosine 0, 0, 0, 1. So just now we have rotated the theta degree about the z-axis. So this is the rotational metrics. So if you rotate upon the x-axis, then you can get this one. And if you rotate upon the y-axis, then you will get this one. So you can see for the z-axis, it didn't move. For the y-axis, it didn't change. And same for the x-axis, is the same. So now comes the problems. So if this is the A frame and B frame, if B frame become like this, then how can we solve this one? Solve the rotational metrics. So the first step is rotate about the z-axis, become here, and the second step is rotate about the y-axis for the y. So it's become here. Do myself. So you can do it by two steps. The first step is rotate about the z-axis, and the second step is rotate about the y-axis. You all understand? Yeah. This can be divided into two steps. Rotate two steps. And so we can write it as this. So rotate about the z-axis for theta and rotate about the y-axis for y. And we just take into, this is the rotational matrix for the z-axis and the rotational matrix for the y-axis. And the chain rules apply. So for A, rotational metric AC is equal to rotational AB times rotational BC. So the question is, will rotational AB and rotational BC equals to rotational BC and rotational AB if we reverse the multiplication? Any answer?
This is the vector. It's a vector component, so we cannot reverse it.
Pardon?
We cannot reverse this because it's a vector.
Yes, that's right. So we have a direction, so you need to follow this direction. You cannot refer to one. So when you're doing the math, you need to really care about the sequence. When you if you go straight, like we do in a translation, go here and rotation, then you're here. But if we do the rotation first, and you go straight, you'll end up in different configuration. So this is a typical rotational joint robot. So we can see here, this is theta 1 and theta 2 and theta 3. So we have the R03 equal to 0, 1 times 0, 1, 2 times 2, 3. And before doing any calculation, you need to set up your coordinate space, your frame. This is you need to set up the x, y, z first, so you know what is your direction. So we can just quickly do 2 examples. You can try it yourself first. Maybe we'll take 5 minutes, or you can just, first you need to set up the coordinate systems, then doing the rotation. This is the first rotational joint, and here will be the second one, and here will be the third one, and here will be any factor. So you want to find this the orientation with respect to the base. So I'll draw the diagram first. So we can transfer that robot into this sketchman diagram. So first we want to define the base frame. So here we say x0, and usually we'll if this a rotational joint, the joint axis is the z direction, and for linear actuators, this is the joint axis. So you will move like this one and back and forth. Okay. So this will we generally will take this this direction as the axis. And if we have determined the two axes, then the last axis can be determined by a right-hand rule. So it's z to x. So it's like this, z to x. So the term will be your y. So you guys can find the orientation of the frame 3 with respect to the frame 0. Or do you want to do a calculation, or I'll just do it? You want to try? Okay, I'll do it this one. So first, we need to set up all the coordinate systems. So that's just how we stated that this direction will be the z-axis. And for the next module, we'll teach you how to set up a special coordinate system called the BH. But for this class, we just set up by yourself. So is it clear, or should I draw larger? Can anyone see it? So this is the z1 axis, z2 axis, and z2 axis. And this here will be, the x direction will all be the same here. And the y is pointing upward. So here will be the 0, and 1, 2, and the 3 is the main factor. So what we want to find is the frame 3 with respect to the 0. So by the chain rule, you can write it like this. And now we'll do the first one. So from here, you can see that z-axis is pointing upwards for the 0, and z-axis is pointing in this direction for the z1. So it rotates about x0 for 90 degrees. So it's like this, and we count this. So maybe I'll draw larger. So and count this. So it rotates above the x0 for 90 degrees. So the first one is basically how you set up your coordinate system. And as this is a joint, so you have a rotational is theta 1, because this is a joint. This one is a joint, so we have a theta 1 rotating angle. So it rotates about the x-axis. Then we can see that 1, 0, 0. And for cosine 90 is 0, and sine is 1. So just putting the number into this three. So it's rotate along the x-axis, then rotate along the y-axis. So you can say this direction is rotate about the z0, or you can say it's rotate about the y-axis, because it's just all pointing upwards. And if we look down the multiplication, it will become this one. So this matrix will be a rotational matrix for the R01. And for here, since the configuration of the axis didn't, the configuration of the coordinate system didn't change. It's always y pointing outwards and z at this direction, and here will be x. So the only effect, the angle will be this theta 2, and also here we'll have the theta 3. So we can write it as this rotate about the z-axis, or you can write it about the y-axis. Okay. So this will be the rotation matrix for the the frame 1 to frame 2, or you can say frame 2 respect to the frame 1. And for 2 to 3, it's the same. So it's rotates upon the z2 axis direction of the rotation metric is also same as your right hand. So this is the x direction, and this will be the positive direction for this rotational joint. And similarly, we can just find the numbers for theta 3 to the z rotational matrix. So I think we have already completed all the rotational metrics from the 0, 1, 0 to 1, and 1 to 2, and 2 to 3. So if we times together, then you'll give the 0 to 3. Then you can find this orientation with respect to your normal. So do you want to try for the second one? So we want to try for this one. The second one, the box is also 3 joints. So 2 rotational joints and 1 prismatic. So the first 2 will be the same as the last one. So I also give the base frame. So do you want to try to calculate this one, the rule for finding this orientation with respect to the base rate? So here we have theta 1 rotational, and here have theta 2, and here we have, this is the and the prismatic motion will not affect your direction, your orientation. Okay, I think you can just maybe do it during the break, and we'll come back. But the final answer should be the same. And for the next class, we'll introduce a method called the DH method, the Deming encounter. So that is a very fast shortcut method to generate all the metrics. So if you want to use that method, there will be some rules to how you need to define the coordinate systems. So for me, I will define like this. So the z-axis for the 0 is pointing upwards, and for the z1 is outwards, and for these 3, because this is a prismatic joint, so this is the direction, so this z2 will be here, and followed by the n factor is the same. So usually we'll copy the n factor frame from the last one, so generate. So here we come for the R01. So just now we rotate the x-axis first, then theta 1 is rotate about the y1 axis, and now we can change our strategy. If we want to calculate the theta 1 first, then after that then we rotate for 90 degrees. So both are okay. So you should get the same answer as the last one, although we rotate the theta 1 first, then rotate about the x0 for 90 degrees. So this want to show you that no matter you just follow your strategy, all the answer will be the same. So now we're coming to the R1 to 2. So the Z1 axis is pointing this way, and V2 is pointing this way. And here we have a theta 2, so we rotate about the Z1 axis for theta 2 first, then rotate about the Y axis for 90 degrees, then rotate about Z axis for 90 degrees, and we'll be completed. So rotate about Y for 90 degrees is like this. Then rotate about Z for 90 degrees. Y. Okay, so rotate about Y like this, and we'll come like this. So we'll first rotate about Y, then rotate about Z. So this is rotate about Z axis for theta 2, and rotate about Y axis for 90, and Z axis for 90. So we get the rotation matrix from the frame 1 to frame 2. And since that this is the translation, so this is a prismatic joint. It's only doing a translation motion, so the direction will not change. And the coordinate system of the frame 3 and frame 2 is identical. So we can just say that from 2 to 3 is equal to diagonal matrix. So you will not change the direction. So is it okay? So as today we have homework, so you can practice during the homework. We have 6 joint robots for you for homework. But you just need to follow the step. I think it's easy to do this. And now we come to another question, is that if we have 2 frame 1, frame A and frame B, but we don't know what it rotates, we cannot separate into X, Y, Z, and we only want to rotate once. So what is the rotational axis? So if this is only difference in the direction or the orientations, there should be one vector that this can just rotate about this vector and become the new frame B. So this is the unit vector R and the rotate angle theta. And for this rotational matrix, it's called the rotational matrix is R, theta, and R. So as it defined, the frame B is the result of rotating frame A by an angle about the unit vector SSR. So now we want to find what is the vector R. So to find this one, we need to separate a sequence of 3 rotation to bring the frame A to frame B. So first one, we want to coincide the ZA axis to the R, and R will rotate about, for theta, then we will translate back to the ZB axis. So C is to map the ZA to R. It is also a rotational matrix. So this is the ZA, and if we have C, then it will become the Z-axis will coincide with the R. So that is to say that if this one is ZA, and this is R. So if the ZA times so we'll have a rotational matrix C to rotate the ZA to coincide with the vector R. So you can see the ZA will be coincident with the vector R. And the R will rotate about the Z-axis for theta. And will transfer, this is the inverse of C, so it will transfer back to the original and become the ZB. So can you understand this is the 3 steps? So for the real question is that if we want to rotate from ZA to ZB about R for theta, so this is how it's formed. So ZA rotates about R for theta angle, then will become ZB. And we want to find R, so first thing is we map the ZA to R. So this is the first one through C. This is also rotational matrix. So we rotate this one to map the R. Is that this? This is R. The axis is coincident with R. And the second step, since now the R is the Z-axis, so we rotate theta angle. Because now the R is the Z-axis, so we can rotate about the Z-axis. And this is the second step. And the third step is we want to transfer back to the original frame B. So through the Z-1 or the C inverse, then we can go back to here is R, and this will be ZB. So because this is C is mapping the ZA to R, and then rotates about the axis for angle of theta, then multiply by C inverse, C-1, then go back to the ZB. So does it make sense? So this is also just for reference, so will not be the test, so it's fine. But you can just imagine that because we don't know what is R, so we map the Z-axis to the R and rotate, and doing the inverse, then we can back to the ZB. And the flow is all on that. So since that we can write the C as R, because we map this is the global frame, so originally will be 001, and since we map the Z-axis to R, so the Z-axis, the Z direction is the R. And just solving the math. So this is Z-axis, rotatable Z-axis is the rotational matrix, and just times up. And if you don't know how to do it, I also using the MATLAB. You can solve it by the MATLAB. It will give you an answer. Just like this. So here we give you the R times convolution R. So here will give you the answer. So since these are the three orthogonal metrics, so let's plot it together should be I. So we can change it so to this one to I minus R and R transpose here. And this is a symmetry score, so school symmetric. So you can see it's RZ, so here will be RZ and RY and minus RY. So this one should be lowercase, this should be lowercase. So solving for that, this will be a general function for the rotational matrix. So in this matrix, I will be the invariant essence of this rotation. So this is a rotational matrix, and it will rotate about R for theta degree. And you can try if you adapt the R equals to 0, rho 1, which is the d-axis, then what will be the R and theta and d equal. So like Rx is 0, so here will be cosine, and here will be 0, and here will be sine, and here is 0. And this one will be sine, then cosine, and 0. And 0, 0. And here should be 1. So this will be equal to the rotational matrix rotate about the axis. So this is the general solution. But you do not need to memorize it. If you need to use it during the exam, we will give you. And also we can do an inverse. So just how we use the R and the theta to find the rotational matrix, and we can do it the inverse directions. We use the rotational matrix, and we can find the theta. So if you add these three up, is the three can give you like this. So Rx plus Ry plus Rt is 1. So it's 1 minus cosine theta plus 3 cosine theta, so it's 1 plus 2 cosine theta. So just like you can put it simplify, and you can get the theta equal to R cosine. But this is not very nice to use due to the R cosine, because R cosine cannot identify in the only provided value from 0 to pi. And since they have like a square root, the square value, so it's the numerical accuracy when the theta towards 0 will be very bad. So another method is proposed. So if you R minus the R transpose, so this is R1 minus R1, so it's O0 in the diagonal. So here will be R21 minus R12. So you can do just a very simple calculations, then you can get this one. You can see one more example. Like Rx1, Rxy, this one minus this one. So this will cross out, and we'll have 2 RD sine theta. So it is very simple math. and we take the 2 sine theta out, and you have a matrix. It's like this. This is also a smooth symmetric matrix. So from here, if you want to find the theta, this is the arctangent. This is the code for, like, if you use the MATLAB or other software, this is the arctangent tool. So here, this one will give you the theta degree. And this one is coming from here. You can just take the Rx equal to 2, 3 minus 3, 2, and Ry equal to 1, 3 minus 3, 1. And Rz is equal to 1, 3 minus 3, 2 minus 3, 2. So it is just taken from there. So this value is only, you cannot use when the sine theta is equal to 0. And for theta, so since the arctangent with the output value, so it's in the 4th quadrant, so we have the 2 impulse arguments. It's not like a cosine. One is absolute, and another only one has sine. For the tangent, both have sine. So we can, like this. Only when y equals 0 and x equals 0 we cannot define. But in other we can define it. So it's take all the values from the minus pi to plus pi. So it's use the sign of both arguments to define all the quadrants. And this is for the r, for the x's. So just how we have said that we cannot use it when sine theta is equal to 0. So if the theta is equal to 0, then there will be no solution right now. But if the theta is equal to plus or minus pi, then we can use, since the sine theta equal to 0 and cos theta equal to 1 minus 1, so we can use this one, and we can get the r also. Or when theta is equal to plus or minus pi. And all these equations or general equation will give you, so you do not need to reinvent any of that. Since for this module, it's more on concept, it's not to memorize all these mathematical formulas. As if you really do your work, it's all in MATLAB. You just like call the functions. You even don't know what is inside that function. You just need to call that. And now we come to the position. So this is the front A and front B. If we translate for a p distance, then the relative distance can say is the b respect to the a. So I think this one will be quite simple. It is just the projection on the XYZ axis. So we can write it as so it's just the projection. This one will be the x, and this one will be the y, and this one will be the z. So it's just the component on the 3 orthogonal axes. And now we come to the collision problems. So just how we have seen this robot, and seen from the top, and this is how you see that. This is a plane, you can see the plane red and white. And we can solve the position vector. So from P0 to P1, this is P0 to P1, and it's equal to this the A1 translation, and for the y 0, so it's A1 0 0, and for 1 2. So the x is A2 times cosine, and for y is A2 times sine, and z is also 0. And from 2 to 3, this is the theta angle. So it's also A3 times cosine, A3 times sine. So this is a position or the translation matrix or the vector, translation vector right now. It is at this it's at this configuration. So however, so what is the position vector from 0 to 3? Is it all added up? Or is it equal to all added up to it? Can we just add all the translation, the vector up, and we can get from the 0 to 3? Will it be like this? So I think probably not, because it will be wrong. Since the theta 3 is from this one to here, so it is not from the base frame. It is from the frame number, I would say the name, frame number 2. This is the frame number 2. So what should we do for that? So we need to translate the distance or the translation vector back to the original frame, so we can add it all up. We need to use the same frame for all the vectors. So let's say if this P, the P coordinate at the A frame is, say, is PAX, PAY, and PAZ, and the rotational, the rotational matrix is still like this. So we can times the vector to the position vector, and we can get two matrices like this, and this one will be the rotational matrix, and this is the position vector for x. So if we want to add the p, if you want to add if you want to add a position vector in a B frame inside an A frame, then we need to transpose it to A frame. So this one will be the coordinates of P in the frame A. You understand? Or it's I know it's just a lot of the translation of the rotation and the stuff. But in general, so why we can't just add these three together? It's because like this position vector is with respect to the second frame, and this position vector is with respect to the first frame, and this position vector is with respect to the base. And if we want to add the three, then we need to have all respect to the base frame, and we can add them all up. So for this one, it's clear like this one, and plus R0, 1 times P1, 2 plus R0, 1, 1, 2 times P3. Then we can add all together. We need to convert this position vector back to the original frame, so we can add it all. But you do not need to really, this is just concept, you don't need to really doing this math, because afterwards we'll have a 4 times 4 matrix. You will have both the translation and rotation together in one matrix, so you will do it automatically. So this is just for a concept. It's like if we want to do the PA and this is the PD, we want to have 3 position metrics. Will it be faster if we calculate like by this direction, or we have brackets and calculate from the backwards? So because the rotation metric is 3 times 3 metrics, so doing the forwards will be taking longer time. And doing backward, this one will be a 3 times 1 matrix. So backward will be faster. So now we come back to this graph. So this is the frame A, and you have a position, translate, and also the rotation, orientation to the frame B. So the position vector is in 3-dimensional space. So it's a 1 times 3 vector. Px, Py, and Pz. And the orientation or the rotation metric is a 3 times 3 matrix. So I think you have all enough of the rotation and the position vector. So now we come to the homogeneous transformation. The homogeneous transformation is a 4 times 4 square matrix. So it's composed of the rotational matrix and the position matrix. And we just go into the 0, 0, 0, 1 for the last. So as you can see, as a vector, the vector PA is equal to AB and PB. So I think this one should be updated. So it is something like that. So we can expand the fourth row here. So we'll add 1 under the position vector, add 0, 3 0. Here will be 3 zeros under the rotation matrix, and 1 and 1. So this is how we got. And so this one will be the homogeneous transform matrix from A to B. So it's contains the information of the orientation and the information of the translation. So afterwards in robotics, all you need to know is this one. But for the previous is you need to have the concept of how it rotates and how it translates. So the homogeneous transformation matrix describes the relation between the reference frame. So relative pose is equal to position and orientation, and transform the representation of a position vector from a given frame to another frame. So it is the rotor translation. Rotor translation means rotation plus translation for the rigid body operated on vector in three-dimensional space, and it's always invertible. So you can always invert this homogeneous matrix. So A, B respect to A, inverse is equal to A respect to B. And it also can apply the chain rule. So if you want to find the C respect to A, you can just first find the B respect to A and C respect to B. So this one will be the inverse. So for the forward one, if we want to find the position of B back to position of A, it is like this, just all we have always stated. So here will be the transformation matrix. And if we want to find the position of A back to position of B, so here will be BA and RBA. So PBA is equal to RAB transpose times RAB. So it is just, you can just flip it and do times the transpose. And here is also the rotational matrix, you just transpose it. So here we can get, this is the inverse homogeneous transformation matrix. So I already highlighted it under here. So if we want to do the backwards directions, this is how you find your rotation matrix and your position vector. So any question about the homogeneous transformation matrix? And we can come to, like, this is some examples. If we have a reference frame of the wall, this is a wall frame. And this is the base frame for the robot. And this is the end effector frame. And this is the tool frame. So how do we connect all the frames together? Then you just use the homogeneous transformation matrix. So first, the wall to tool, because it's stationary, it's all on the ground, so it's fixed. So this is a constant. So it's equal to the wall to the base. So this is this direction. So it's, you can say base with respect to the wall. So this direction, and from base to end effector, we also can derive a transformation matrix. And here from the end effector to a tool, so we can see is from wall to base to any vector and vector to tool, and it's equal to this direction from the wall to tool. And this is then how do we get our robots transformation matrix? Because what we want to solve in the robot modeling is the reference frame with respect to our base frame. This is the modeling of the robot. Then we can just times the inverse here in front, and it will be cross out, and all times the inverse back here, so it will be cross out. So we will divide this. So it's go to base inverse times go to task, and from the A vector to task. So this one will be a task reference frame. And another problem is for hand-like aggressions. So usually we will have form a closed loop. So we also can form a base frame to the camera because all this can we can calculate. And since the calibration plate is fixed, so we also can find the base frame to the calibration plates. And since it is fixed, so a camera to any factor, the transformation metric can be found. And this is done through the vision systems. So if camera will take the photo of the calibration plates and will map this transformation matrix through some method, image processing method. So are this for the transformation matrix clear? Or do you have any questions about it? So if we have time, we can show you this one. Is this one is a MATLAB toolbox written by Professor Peter Koch. So it is a very good toolbox. I think the school has provided the MATLAB for free for educational use. So where you can download the MATLAB and download this toolbox, and you can play with that. And also for a final project, if you don't have you don't have a platform for your simulation, this can also you can also use this as a simulation platform. So I'll show you how you simulate. So here is the model information for the robots. So basically, it's all the revolute joint and also the link informations. And this is 6 links. So, and here will be the joint, all the joint information. So this one will be joint 1, joint 2 to 6. So this is at the 0 configuration. And this is a serial linkage robot. So this is the model. So I'll show you an example of how to use this. You can just run this model, and you'll have all the information up here. And this is the short for the forward kinematic. And you can see it. For forward kinematic, it also gives us the homogeneous matrix. So if you can see this one, you can see this is an identical rotational matrix. So it shows that the orientation of the any vector is identical to the base. So it is set as the base coordinate frame. And this is the position vector from the base frame to the tool frame. And you can see it. This is the robots. So here is the configuration of the end effector, and this is the global frame. So the x direction is the same, y direction is the same, and z direction is the same. So just now, for the kinetics, this homogeneous matrix here shows the direction of the end effector is identical to the place frame. And we can see it for the x and y and z. This is P. So it's also shown to the homogeneous matrix. So here is the position vector. So I think we should take a break.
Hello everyone, good afternoon. Today I want to present the case study on the underwater robotics. Me, Mohammad Azim and Leonard Robotics have worked on this project. So let's introduce this. This is the first outline what we have mentioned in this case study. The first one is the background, the second one is the structural analysis, after that the application and classification, and the third and the last one is the references. And this is the background behind the underwater robotics. The first question came in our mind, what is an underwater robot? And the answer is the underwater robot is a type of robotic system designed to operate in aquatic environment. These machines can be remotely controlled or operate autonomously equipped with various sensors and tools for specific tasks. There are two kinds of underwater robot exist. The number one is the remotely operated underwater vehicle, and the next one is the autonomously underwater robot. And I will explain later how it works actually in the later on. And the remotely operated vehicle are controlled by operator on the surface, while AUVs operate autonomously. They can perform various tasks such as inspection, maintenance, repair operations, scientific research, and search and rescue. I will explain later on how it will work. And why need we underwater robot? What's the reason why we need this one? The deep sea is the last unknown frontier on our planet for humanity. Although subsea technology has progressed much, 80% of the ocean remains unexplored. Location for extracting oil as gas can be extremely deep inside the ocean. It is risky and even impossible for human divers to perform site exploration, infrastructure, inspection, intervention and repair. With the increasing oil price and decline in land deposits, there is rising demand for offshore exploration and mining. Infrastructure installation, maintenance and repair. That's why we need the underwater robot. There are many more things, but I didn't mention why we need this kind of it. And there is a history behind the underwater robot. The first remotely operated vehicle ever built was the Poodles made in 1953 by Dmitry Revikov. It was a French pioneer in dive equipment and photography. And this is the first autonomous underwater vehicle. The previous was the remotely operated vehicle. This is the autonomous underwater vehicle. The first AUV was developed at the Applied Physics Laboratory at the University of Washington as early as 1957 by Stan Murphy, Bob Francis, and later Terry Award. The self-propelled underwater research vehicle was used to study diffusion, aquatic transmission, and submarine away. This is the image of the first AUV. The US Navy started using ROVs in 1960s for recovery of underwater equipment and continued to advance the technology. By the 1980s, there were more than 500 ROVs around the world, many of them being used in commercial applications. Since the ROVs have become common in a wide range of industries, and there are 10,000 of ROV users around the world. In 2021, the US Navy was allocated $1.6 billion for research, development, testing, and evaluation of autonomous underwater vehicles. and almost all the countries are investing now in the underwater, on the research or on the underwater robotics. Now I am going to move to the second part, which is the structural analysis. This is some images of underwater robotics. This is autonomous underwater robotics. It was my last project in my university, bachelor university, what I have worked on underwater robotics. And this is the few images of that. It is a dual hull single camera vision guided AUV with 5 thruster with a maximum 5 degree of freedom. The dual hull means this is called hull, this is called thruster, and we have vision guided and with 5 degree of freedom. And this one is the connections of all components. The first one is a battery send the power to the power distribution board, and power distribution board and supply the power to the buck converter is send the power to the Jason Xavier, and camera send the signal to the Jason Xavier, and the next one is send the pick sock, and the leak sensor and pressure sensor also send the data to the pick sock, and after that he, according to that data, he controls the speed of thruster. And now we move to the embedded system. If I show you, in these hulls we have in the single one we have put the battery, and the second one we have put the embedded system. We use the delta type try to use the electronics item and embedded system. On the phase first we have installed the Pixar and Intel Sense camera. And on the second phase we use the Jason Xavier, and on the third we use a 4-in-1 ESC and Blue Robotics and buck converter. And now I want to classify the electrical component. UV electronics are powered by two 8000 mAh 11.1 volt lithium polymer batteries connected in series to provide a total volt of 22.2 volt at 8000 milliampere hour. The power is then fed to the power distribution board, which provides 6 output of 22.2 volt of each. It provides us 6 power distribution, 5 goes to the thruster, and the single goes to the buck converter. After that it goes to the Jason Xavier. And 5 are that's all. And now we move to the thruster control system. We have used the 5 Blue Robotics T200 thruster, which has used brushless DC motor. As previous professor said, what is a brushless DC motor? And for the waterproof, we use the epoxy resin to make a waterproof, because it goes underwater. When water goes inside the brushless DC motor, it will burn out. That's why we enclosed in a chamber and sealed with the epoxy resin. At 22 volt, they take a 32 ampere and provide a thrust of 6.7 kgf. Two different types of electronic speed controller are used which send a pulse with modulation signal and which control the thruster. One is Sky Stars KM50 Pro 50 ampere 4-in-1. This is the specification of the electronics speed controller, and another is the Blue Robotics. The ACs are controlled by the Pixar autopilot board employing the Arduino plot, Arduino sub control surface. Arduino sub works seamlessly with the ground control station software that can monitor vehicle telemetry and perform powerful mission planning activities. And this is the flowchart of the control system. Camera sends the data to Jason Xavier, and Jason Xavier sends the data to Pixar, and pressure sensor and link sensor also send the sensor to the data to the Pixar. Then it further moves the ESC, and according to control his speed to the thruster and move further. Jason Xavier, this is the specification of Jason. What is Jason Xavier? Jason Xavier is specially designed for autonomous machines. It features octa-core ARM64 CPU and Volta GPU architecture. With up to 30 TOPS processing power, it is ideal for path planning algorithms, sensor fusion, visual odometry, and localization of mapping. Pixar industry-leading open source autopilot platform. It incorporates high-performance hardware with a user-friendly interface, making it versatile and reliable. It is also open source, which encourages community contributions and adaptability. This is the sensor what we have used. Attitude, heading and reference system. The Pixel comprises MPU 6000 as a main asset and gyro. ST micro 16-bit gyroscope, ST micro 14-bit accelerometer, and NIST barometer. The combination of these sensors provide accurate and stable data. And now we have to use the pressure sensor. The blue robotics bar 30 pressure is used for precise pressure measurement. It can measure depth up to 10 meters with a depth resolution of 0.16 mm. And this is the camera what we have used. Intel RealSense depth camera D435 provide high quality depth for a range of applications. For applications like a robot, augmented and virtual reality, where seeing as much of scene as possible is crucial. It has a range of up to 10 meters and comes with Intel RealSense XDK 2.0 and cross-platform support. And there is also we have used the leak sensor. The leak sensor, the SOS leak sensor can detect water leaking into the improperly sealed watertight enclosure quickly and reliably before any major damage can occur. We also use the kill switch for to stop the underwater to performing the underwater robot in such emergency cases are like that. The magnetic reed switch is used to travel a 60 ampere relay which is between the battery and power distribution board. When it is triggered, it disconnects the battery from the rest of the component and protect the component in the case of failure of emergencies. This is the stack structure, how it will be about. There are three different types. We classify the structure in the three different. The software module, navigation module, and the control module. In the software module, it receives live input from the camera to guide the vehicle. We also use the YOLO V7. It is a real-time object detection model. It receives a live input from the camera to guide the vehicle in accordance with the assignment given by the task planner. Subsequently, multiple pre-processing steps are applied to enhance the image quality, followed by image processing algorithm to extract the features and obtain a guide data. And now we move to the navigation module. It takes the guide data published in the software module along with other data from sensor and calculate the relevant actuators, command values accordingly. And now we move to the control module. It is responsible for controlling the 5 thrusters, for maintaining stable motion and position of the vehicle using the PID algorithm and transmitting the PWM values to the ESC. Now move to the application part. Leonard will further move with this one.
Thank you, Ashley, for the good introduction on the water robots. Now, quickly check the time, so we don't have that much time left. I will wrap it up quite fast. So, going quite through it. So, for what do we need underwater robots? So, for example, idea. The marine research, so we want to know, because we already told you, 8% of the ocean is unexplored, so we want to see what is down there, making geographics, collecting samples, study underwater structure. And here's the, for example, the Eugene, what was used for that. Then the offshore industry, because it's kind of rough for divers to work underwater, so these machines, these underwater robots can, for example, inspect, maintain, repair on offshore oil platforms and pipelines. Then the military is really interested into underwater robots because these robots can detect underwater mines and if the robots are big enough, they can also attack submarines or ships. And the US Navy classified 4 different sizes of that. The main portable is the size between 10 to 50 kilograms, then the lightweight between up to 277 kilograms. The heavyweight is already 5,000 to 10,000 kilograms, and the extra large one, that's kind of a smaller version of a submarine, weighing more than 10,000 kilograms and can attack warships and submarines. Next off, we have the resume and salvage operations. So, for example, what this Jason Jr. AOV was used to explore the Titanic and see how it looks down there, if something changed. And for the environmental monitoring and conservations, here this AOV Anton was used to see if the coral reefs are, for example, how they look, is the reef health, how's the water quality down there, and how's the temperature, and can we maybe help the reef, and what can we do for that so it still survives because of the climate change. Then last of the archaeology and underwater exploration to see how the, for example, shipwrecks look like now and how maybe already saved cities looks, and to just have an idea how the history was a few years, 100 years, 1,000 years ago. Then last of all, the classifications. Like Ashing already told you, there are two different kinds. There are ROVs that are connected with an operator on the surface, so the operator has all the time control about them. And then the second one is the autonomous underwater vehicles, so they can operate by their own. They're using all the sensors to navigate through the ocean by their own, so no operator is needed. And last of all, we have a hybrid underwater vehicle, so a combination of both. So, for example, maybe you will start your mission with an operator, you will let the underwater robot go and sink, and when it's on the right position, you will just loose them, and then we can operate by its own. So, that's it. So, for a summary of our presentation, we told you about what are the differences between ROVs, AOVs, and HOVs. So where we should use them, why we use them, because it's safer to work with a robot than a normal diver has to go under the sea and work, maybe do some buildings or find some mines also. Then what are the benefits? Safer, efficient, and for the future impact, the industry is really interested in it, and also for science research. Thank you for your attention, and the last few pages are just our reference. If you are interested in them and want to know more of that, we can send them to you.
So, any questions? Okay, so I'll jump a few questions. So, very complete reports in case you are studying for that. And so, just a simple question is that after your classification and all the applications, what do you think, what is the future trend for the underwater robots?
Actually, nowadays many militaries are using AUVs as a weapon nowadays. There is militaries are already invested too much as a weapon to attack to stop the attacks on the submarine and like that. And there is mainly the underwater robots are using in the offshore industry. Offshore industry, you know the offshore industry? Offshore industry, oil, to extract the oil and gases from the many oil and gases are extracting from the sea, which is hard to go someone inside the water or inside the sea to explore the things where is the oil and where is the. That's why it's very challenging for the human. That's why we develop a robot which go inside the water and then we attach some kind of probe, and like that we go underwater, explore, take the images and take the samples from the probe, and the engineers will take the data. If we find there is a gas or oil inside the water, then they will implant a plant to extract the oil. Either select the random place to extract oil, it will be very costly, and that's why this is mainly used in the offshore industry.
Thank you.
Okay.
Any more questions? Okay.
This one. So the next group.
Hello everyone. Today we will be presenting work in social environments. These robots are designed to understand human emotions, language, and behavior, allowing for natural interactions, unlike traditional robots that focus on efficiency. Social robots aim to engage emotionally and socially with humans. They are commonly used in areas like education, healthcare, entertainment, and customer service to improve relationships and enhance people's life. Structure analysis of data. Data is a social robot equipped with a variety of sensors and actuators that enable it to interact with its environment. It has touch sensors on its head, hand, and lower body for detecting physical interactions. It also has a 3D camera on its forehead and 2D cameras in its eyes to see faces and recognize gestures such as waving. Through the integration of computer vision and computational neural network, CNN, paper can recognize the waving gesture in real time and respond by waving back, enhancing
includes motors, actuators, and various sensors, such as 2D cameras, 4 microphones, and ultrasonic distance sensor, infrared transmitters and receivers, an inertial unit, 9 touch sensor, and 8 pressure sensor. This device help now perceive its surroundings, recognize object and effects, locate some source, and interact with human. Through speech now processor from the Linux kernel and support Wi-Fi and the Internet connection, allowing the remote control and application development. VIA is SDK. Its movements are based on a linear inverted pendulum model and inverse kinematics, enable balance control and fall protection. The application of now. Now's applications cover education, research, business, healthcare, service, and the entertainment industry. In education, now is used to teach programming and robotics, allowing students to learn through hands-on practice. In research, it is employed for human-robot interaction, speech recognition, and behavior modeling. In business, now assist with customer service, providing information and entertainment, while in healthcare, it helps with therapy for autistic children and the elderly. In the service industry, now with and guides visitors in places like hotels and airports, improving customer experience. In entertainment, it performs dance, plays interactive games, and engage in storytelling, enhancing brand appeal. Thus, versatility makes it valuable across these diverse fields. Here are the main characteristics of social robot. Human-robot interaction. Social robots are designed for effective human-robot interaction. They engage with people in a way that feels natural and by understanding and responding to human emotion, gesture, and speech. Independent operation. This is robots can operate autonomously, performing tests and making decisions based on their programming and real-time environment inputs. Context-aware, adaptability. Social robots adjust their behavior and response according to the context of their interactions and the feedback from users, ensuring their action remain relevant and appropriate. Emotional sensitivity. Their post-emotion sensitivities, allowing them to recognize and react to human emotional states, which helps in fostering supportive and meaningful interactions. Human-like socialization to enhance user engagement. Social robots mimic human social behaviors such as eye contact, facial expression, and body language, creating more relatable interactions. This is our reference. Thank you, Professor and classmates, for listening.
So any question for this, for social robots? just have a quick questions. So, in general, what would you think it is? What is the critical components for social robots to interact with the humans?
Component for social life to interact for human.
Yes. What are the components? The critical components. So it may be some sensors or some stuff you need to have that so you can interact with the environment or the humans.
I think touch sensor and microphone and camera is the best for social robot because it needs this is sensors to recognize the human actions and gesture, and it can use their modeling to give human reaction.
Thank you. So I think maybe due to the lack of time, limitation, I think we only have like 13 minutes to break. Maybe you can postpone to the next week. Is it okay? So next week we will start earlier. So next week we will have 4 groups. So because so and this week you have homework. So I think we still have like 10 minutes. I will introduce our homework for this week. We have 6 questions, and you only need to answer 5 to get 4 marks for your homework. So one will be extra. You can write, and we will count the highest score for the 5 questions. Or you can just leave one blank if you are very confident that you can all score very high. So all are very simple questions, and the first 2 you just listed, and you don't need to write very complicated, because you just list the common sensors, the physical qualities, and the second one will be the advantages and disadvantages. You can just compare it by yourself, and you can know what actuators you want to choose when you want to design a robot. And the third one is I think this is in the lecture notes. All the calculations is for Bristol Bridge, and the fourth and fifth, the fourth will be determine the 2 solutions. So this is the rotational matrix, and you want to find the vector r and the theta degree. So you will have 2 solutions, and the fifth one is the rotational matrix, and the 5 and 6 will be compulsory. Because I want you to do these 2 questions. And the 6 is do the transformation matrix. So I think any problem for work? Or do you think it's too much? Too much? Then at least do 4, 5, 6. Yeah. Then it will be fine. At least then the extra will be additional marks if you start to you may the 1 to 3 will be additional. Is it okay? And then will be 10% and 40% and 40%. And this will be additional. And for question 5 and question 6, you need to label all your configurations. So for question 5 and 6, you need to label all your configurations systems. So like from 0 and 1, 2, 3, 4, 5, 6. So I've given you the first one and the last one, and you also need to label yourself for the local frames.